So in this video, we're going to take a look at making a piecewise defined function continuous. So in this example, it says find a constant a that will make the function continuous over the rails. And so we're given a piecewise defined function. It's defined in two pieces. Each piece is defined over a specific interval. So for x less than or equal to 1, we're really saying that the x's can run from negative infinity up to 1 inclusive. And for x greater than 1, we're saying this function takes over on the open interval from 1 to infinity. So if I just thought about drawing this for a minute, this is a cubing function, and it only gets to run up until x equals 1. So if we just think roughly about what the picture would look like, the toolbox function sweeps up, comes through the origin, zips up, and when x equals 1, this is going to need to stop right here, and we plug 1 in here. We get 1 cubed is 1 times 3 is 3, so it's going to be an output of 3 sitting right here. And we're going to have the point input 1, output 3. And then we think about what x plus 5 looks like. Well, this is this is a linear function. The toolbox function would be y equals x. It's a linear function shifted up 5 units, so it's going to have a y-intercept up here at 5, and the slope of it's going to be a. But it doesn't get to run everywhere because it only gets to run for x greater than 1. So somewhere up here, there's going to be a hole because x can't equal 1, and then this function is going to zip off with a slope of a units. And so the problem is if we don't choose a wisely, these two functions won't connect. We'll have a jump discontinuity. And really what we're being asked to do is to find a value of a that keeps this jump discontinuity from happening so that this linear function picks right up where the cubing function leaves off. That's our job, is to figure out how to connect the two functions up so that we could draw the picture as one nice continuous picture. So the way that you do it is you want to recognize that, oh my word, come on. You want to recognize that they need to share the same output at the boundary. So even though this function doesn't get to receive an input of 1, we want it to give the same output or generate the same output when we input 1 as this one generates when we input a 1. So the key is, hey, plug a 1 into this cubing function because we can, and see what the output's going to be. And then, even though we're not supposed to plug 1 into this function, plug a 1 into the linear function and see what value of a will force it to have a matching output at 1. So we get a times 1 is just a, plus 5 equals 3. And then we subtract 5 from both sides, we get a equals negative 2. So we actually see the picture that we're getting. We're coming up, and then at 1 we're going to stop, and then we're going to have the linear function connect up right there and dive down with the negative slope. So we could update this. We could say, hey, now we have a function f of x equals, it's a piecewise defined function, 3x cubed for x less than or equal to 1, and that should match up as long as we do negative 2x plus 5 for any x greater than 1. So it's just a matter of finding this value so the two functions hook up with each other and we don't get a jump discontinuity in the piecewise defined function. So here's another example, and the principle is the same. When x is 0, we'd like these two functions to match up. This time there's a problem, though, that we didn't have in the previous example, and the problem is that we actually can't plug x into this function because we would get a division by 0. So what happens is we need to know what output the function is approaching as x approaches 0 because we're unable to put x into it. And so what we want to do is hey, this is for x less than 0, right? So x is coming from negative infinity running up to 0, but it never gets there. So let's take the limit as x goes to 0 from the negative side of 4 sine x over x, and then think about our limit properties. We know that by our limit properties, the constant can pull out front. We get 4 times the limit as x goes to 0 from the negative side of sine x over x. But this is a limit that's been calculated already to be 1. So we get 4 times 1 is 4. So this function, even though this part of the piecewise function, even though we can't plug 0 into it, gives us an output that's approaching that approaches 4 as x approaches 0 from the negative side. So once we know that this function's trying to give us an output of 4, we want this to match up when we plug in 0. So we plug in a minus 2 times 0, plug that 0 in, and say, hey, we want to force it to be 4 so that it butts up with the other function. So we wind up just getting a equals 4 when we solve this. So the final function then is f of x equals 4 sine x over x, and we get 4 minus 2x, and this is for x less than 0, and this is for x greater than or equal to 0. And of course the way that we could check our work would be to graph the piecewise defined function, for example in GeoGebra, and make sure that we actually had a function that looked continuous over the real numbers.